Okay, so we want to do examples. We want to calculate partial derivatives. And here's the definitions that we wrote down. This is a reminder. Just one thing I forgot to say, the notation for the partial derivatives, if you happen to notice, the regular d that was in single variable Leibniz notation now changes to this squiggly d sort of thing. Looks maybe like a human ear or something like that. And that's the notation used. Okay, so whenever it's a function of two variables or more, we're going to use this this notation. Okay, and so it's not just a mistake that I didn't write this. Whenever you see this, this is a derivative of f with respect to x, but here f is only a function of x. Okay, clear? Okay, let's do an example. Let's calculate some partial derivatives. So here's the, maybe we'll start on a new board. Here's an example. So let's look at the function f of xy equals xy divided by x squared plus y squared. This is whenever xy is not the origin, and 0 at the origin. This is a function that we've already met. Okay, and what we did with it was we calculated, we explored if it has a limit at every point. Obviously, it has a limit at every point which is not the origin, because it's just an elementary function, so the limit is plug in the point a, b. And at 0, we found that it doesn't have a limit, because as we approached along straight lines, remember? As we approached along straight lines, we got different values. Okay, so that's when we first encountered this function. And now we want to calculate partial derivatives. So first of all, let's start at a point which is not the origin. Okay, just at any point x0, y0. So what is the derivative of f with respect to x at some point x0, y0, where x0 and y0, x0, y0 is not the origin? So what am I doing? I want to take the limit, I want to use that definition, right? But that's just the regular definition of the derivative of this expression where y is fixed, right? So y is fixed. Think of y as a parameter a, and you want to take the derivative of this with respect to x. That's precisely what we're doing, okay? So I don't need to resort to the definition. I can use all the theory that we already know for taking derivatives of functions of one variable, okay? Y is now fixed. Y is the fixed value y0. I'm taking the derivative with respect to x. It may be confusing in the first couple of times, but then it's just completely standard. You'll do it without thinking twice. Okay? So with respect to x, y is fixed. Do you see here that this is a quotient? So I need to use the quotient rule, right? So how do I use the quotient rule? I need to take the derivative of the top. What's the derivative of the top with respect to x? Y. Times the bottom, x squared plus y squared, minus the derivative of the bottom with respect to x, 2x. Y is a constant now. Y is fixed. Its derivative is 0. Times the top, untouched, divided by the bottom squared. And all of this I have to evaluate at the point x0, y0. Is it clear what just happened? I regarded y as a constant and x as the variable. That's precisely what's been going on, what we discussed. Okay? And do you know this notation, evaluated at? Have you seen it? Okay. So what we get is, what do we get? Do things cancel out here? I have what? Well, let's see. I have yx squared minus 2yx squared. So it's minus yx squared. But remember, I'm evaluating at x0, y0, so I'll already write that. And then I have plus y cubed, so plus y0 cubed. And then divided by x0 squared plus y0 squared, all of that squared. That's what I get. Is it clear what just happened? Okay. And similarly, you could do the same thing for the derivative with respect to y at any point, x0, y0. I don't want to do that calculation, not because I think it's not good to do more than one example, because it's precisely the same calculation, because this function is symmetric in x and y. So it really will be boring. Okay? Clear? Everybody good? So this is for points which are not the origin. What happens at the origin? At the origin, even if it were an honest single variable function, at the origin, I can't just use rules for differentiation, right? Because it's defined differently, right? I have to resort back to the definition. Do you agree? Okay? Even if it were a single variable function, I have to use the definition when I want the derivative at 0, or at 0, 0 in this case. Okay? So that's what I'm going to do. I'm going to resort to the definition. I'm going to do it on that board where we have the definition. Just remember what the function was. Okay? xy over x squared plus y squared when it's non-zero, and 0 at 0. So let's continue the example here. So the derivative of f with respect to x at the point 0, 0, I have no choice but to use the definition, this definition. Okay? So it's the limit as h goes to 0 of the function evaluated at x0 plus h fixed y0. And remember, both x0 and y0 are 0, right? So let's do an intermediate step. So it's f at 0 plus h, 0. That's this thing now, right? Minus f at 0, 0, divided by h. Do you agree that this is the limit that I want to calculate? Good? That's because the point is 0, 0. Now I want to replace this f with the actual function that I'm looking at. And the function was, so it's the limit as h goes to 0 of, the function was, at points which are not the point 0, 0, like this point, I have to plug in h for x and 0 for y, right? And the function was xy divided by x squared plus y squared. Okay? When I plug in h for x and 0 for y, I get 0. Do you see that? Because it's h times 0 divided by h squared plus 0 squared. It's 0. So that's this 0 here. Here I need to evaluate the function at the point 0, 0, and that was 0 by definition. Right? Minus 0 divided by h. 0 minus 0 is 0, divided by h, which is not 0. So all of this thing is 0 for any h, and then the limit as h goes to 0 is 0. Questions on this? Is it clear? Good? And similarly, you can do this calculation. Again, it's completely analogous. Similarly, the derivative with respect to y at the origin is 0. Okay, questions? We will, of course, do more examples, but is this example clear? Okay. Now, even in this first example, which was not difficult, everything was rather easy to calculate, and you just have to notice and to understand that at the origin you have to use the definition. You can't just use product rules or whatever. There's something that you should notice, okay? And that something may be strange at first glance, but we'll discuss it. We have derivatives. Do you see that? We calculate them. They're 0 at the origin. Do you agree? What does it mean that they're 0? if you look at the origin, I don't know what the graph looks like, but at the origin, remember we had these two lines here, that the picture is still up here on the board. Look here a second. Now we're looking not just at any point x0, y0, but we're looking at the origin. But still, at the origin, we're going to have this line and this line, right? And these lines are just of slope 0, right? So they're, one is like this and the other is like this. Do you agree? That's that plus that we're getting sitting up here. Remember? And it prescribes a plane which is going to be a flat plane. Do you agree? That's what we just found out. Okay? But something is weird here. Remember, regarding this function, the first thing we said about it is that this function does not have a limit at 0. Look here for a second. This function does not have a limit at 0. Ami, here, thank you. This function does not have a limit at 0, right? If it doesn't have a limit, it's clearly not continuous, right? Because the basic thing in being continuous is having the limit equal to the value at the point, but it doesn't have a limit. How could it have derivatives? One of the most elementary theorems in Calc 1 was, if a function is differentiable, then it is continuous. Remember that theorem? So here something weird happens. The function is not continuous. It doesn't even have a limit. It fails continuity for the most basic reason, okay? But it has those derivatives. And I'm doing this, okay? So somehow this notion of partial derivatives is only capturing a part of the phenomenon. It's not good enough in that sense. Is it clear what I'm saying? Okay, so let's write that. Remark. In this example that we just did, f, or let's write the derivative of f with respect to x at 0 and the derivative of f with respect to y at 0 both exist. Although the limit as xy goes to 0, 0 of fxy does not exist. And therefore, f is not continuous. Is not continuous at the origin. So the most basic thing you would expect if Calc 2 generalizes Calc 1 is that derivative implies continuous, okay, or differential implies continuous. And it seems to fail, okay? And the reason is that things get more complicated. Having partial derivatives is not enough, okay? And we're going to have a notion of being a differentiable function. We're going to have that notion. And it's going to be something asking more than just having the partial derivatives. Okay, so every differential function will have partial derivatives, but not every function that has partial derivatives is differentiable. Okay? And once we set up that notion of being differentiable, which is a bit more challenging notion, then we're going to have a theorem that says if f is differentiable, fxy, if it's differentiable, then it's continuous, and things are going to work. Okay, clear? Now, how could that be? How could it be that it has derivatives, that plus is sitting up there very nicely, and still something goes wrong, right? It doesn't even have a limit. How could that be? So the reason is that these partial derivatives only look at what happens along one straight line and another straight line, right? The x direction and the y direction. Only these two lines. That's what we're looking at. Do you agree? And everything that happens between these lines, for example, along a diagonal line, those partial derivatives don't detect. Okay? So the function can be very nice along these two lines and terrible between them, and the partial derivatives won't know that. Okay? That's why the partial derivatives are not enough. Is that idea clear? Okay? Now I want to draw a picture that would somehow maybe convince you of that. I think it's an illuminating picture to see, but it's not a terribly easy picture to draw. Nevertheless, I'll make the effort. So think of here's our perspective drawing. So think of a roof of a building. Okay, so this is like a building, and it has a nice roof that looks like this. This is the building. Oh, I think it came out pretty convincing. One more line missing. And this should be maybe... Oh, that was okay, I guess. Is it clear what you're seeing? Okay, think of a big old farmhouse, I don't know, with some shape like this, or a church, or I don't know what. And you're looking at this point here on the roof. Okay? And think that this is the y-axis and this is the x-axis. Do you agree that when somebody is walking along this roof, maybe a cat, and he's just walking along a flat line? Do you see that? The partial derivative of the function with respect to y, with respect to x, at this point, or it's at this point, this is the graph, is 0. Do you see that? That's this. If the cat is walking in this direction, in the x direction, okay, well, in the minus x direction, again, he's walking along a straight line. Okay? Non-effort. Do you agree? So there really is a plus sitting up here, okay, in terms of those lines that are given by the partial derivatives. Do you see that? However, if you look at any other direction and you take a cross section and have the cat walk, he would be walking up and then sliding down. Do you see that? Okay, it would be an honest cusp. So any cross section, if you would draw just a cross section, what you would see is something like this, a cusp. Okay, so this, just looking along these two lines, you get a false image, a deceiving image of actually being able to put a tangent plane and everything is nice and smooth. But this is completely non-smooth. This point is... Okay, clear? Is the idea clear? So there is no tangent plane at this point. Okay, well, it sits along these two lines, but it's not tangent in any other direction. Clear? Is the idea clear? Okay, so the bottom line of this discussion, and did everybody understand what I drew here and what the idea I was trying to convey was? Yeah? Everybody? Okay, so the bottom line of this discussion is the following. We're still missing a key definition, a key concept, and that is whatever differentiability has to be. Okay? So there should be, and there is gonna be, a notion of being differentiable, which we haven't discussed yet. And being differentiable is going to imply, so this is kind of a spoiler for the episodes to come. This differentiability is going to imply being continuous. And it's going to imply existence of the partials. Let's write it like this. Imply existence of the partial derivatives, d to dx and d to dy. Both of these are going to be implied by that notion of being differentiable. However, these two don't imply each other. Being continuous is not going to guarantee existence of partials, and existence of partials is not going to guarantee continuity. Example for this being false, we just saw, right? The example we did in just a few minutes ago was where partials exist, but the function is not even continuous. Here, at least, it's continuous, okay? In this drawing, at least, the function, whatever it is continuous. In the example that we saw, it's not continuous even. Clear? Okay, everybody with me? Okay. So what we want to do next is somehow be able to define that notion of differentiability and then see how that gives us the phenomena we want to capture, the existence of a tangent plane. Okay? That's coming up next. Cool drawing.